5.1, areas and distances. The objective of our lesson today is to find the area under a curve. So in this diagram, we want to find the area of S. Our idea, as with derivatives earlier, is to use a limit of approximations to arrive at the true area. So what do I mean by that? We're going to first approximate, just like when we were doing derivatives, we first approximated the derivative and then we were able to find it. So now we're going to go backwards. We're going to first approximate the region S by rectangles, and then we're going to take a limit of the areas of these rectangles as we increase the number of rectangles. What in the world do I mean? Let's look at the figure here. I'm saying that in order to find the area under some curve, we're going to just approximate it by drawing rectangles underneath, and of course we can find the area of that rectangle. In our figure here, what do we know so far? We know that y equals x squared, and we know that we want to find the area between x equals 0 and x equals 1. So basically, if we drew one humongous rectangle here, right, our area would be 1. So right off the bat, we know that the area is between 0 and 1. Again, I just know that because, of course, it has to be greater than 0, and then if I made one humongous rectangle here, that area would be 1, and it's clearly less than that. What else do I know? Well, let's look here, and we drew these rectangles by using what we're going to call right endpoints, because I took my right point, I took the point at the right, okay? So I took this right hand point and I made a rectangle to the left. So I took this point, the value here on the curve, and I used the right end point to make my rectangle. So there's 2, took this point, I just went over to my next point, and again. So this is going to be called right endpoints. And how many did I make? I did 4 of them, so I'm going to just abbreviate that R4, and you'll be seeing me use that notation in the future. Well, what is the area using R4? Well, the area is just the base times the height. So my first height is the function value at 1/4, right? So the width is 1/4, and the height is the function's value at 1/4. In other words, f of 1/4. My next width, well, all my widths of each rectangle is 1/4, right? So I went 1/4, 1/4, 1/4, 1/4. So then I do the width of my second rectangle. Okay, so that's that one. Times f of 1/2, because that's what I used as the height of my second rectangle. Width times height. That's that one. And then this one, I just used f of 1. Okay? And so what does that come out to? Well, f of 1/4 is just, my function was y equals x squared, so 1/4 squared. Then I'm going to do 1/2 squared. And that should work out to 15/32. So that is the area of just the rectangle. So I'm approximating the area under the curve with these rectangles. Now that's clearly an overestimation, right? If I use the same logic here, using my left end points, when I make 4 of them. So basically I'm going to pick up the left point and then I'm going to go over. So my first rectangle, it looks like it's not there because, you know, I didn't go up at all. And that was my first one. Here's my second one. So just go over to the next endpoint, and my delta is 1/4 here. I'm just choosing to make 4 of them. So 1 divided by 4 is 1/4. That's how I know the width of each of them should be 1/4. Okay, and then my next point is here, so I just go straight over. Okay, and then my next one's here, and I just go straight over. All right, there are my 4 rectangles. The first one's not existent, but I still have 4 rectangles. And so the area here, I'm just going to write it underneath. Same logic. The width is 1/4. And the height now is just f of 0 because I start at the left. My second one is at 1/4. My third one is at 1/2, and my last one is at 3/4. You see that? Because I'm going left. So that's the last one that I make. So first, it's my second, here's my third one, and here's my last one. And that should come out to 7/32. And that is clearly an underestimate. There's a lot of white space here. And so what we've noticed, just kind of numbering this so you see my logic, is as we increase the number of rectangles, we would be getting a better approximation. Right, and in each of these cases, we only use the 4 rectangles, so our approximation isn't really that great. And what else can we notice, just based on what we have so far? We know that the L4 was too small, and our R4 was too large. And this is always true when we have an increasing function. And we'll talk a lot more about that as we go on. So here's kind of getting at what I was saying in point number 4 in the previous slide. If we make 8 rectangles instead of 4 rectangles, then our delta x now is just 1/8, because 1 divided by 8 different rectangles would be 1/8. And you can see that both of these areas are a much closer approximation to the actual area under the curve than what we saw previously. And if you make even more rectangles, so I'm making 1/n the delta, I'm splitting into n different rectangles, you see that we get much, much closer as we increase the number of rectangles. So just as a definition, we define area A to be the limit of the sums of the areas of the approximating rectangles. The width of each of these strips is given by delta x, which equals b minus a over n. All that's saying is you take the end minus the beginning, and then you split it into n different strips. And so the width of each of those strips would just be b minus a over n. So let's, for example, say that we're going from 0 to 5 with 5 rectangles. Then what would our delta x be? Our delta x would just be the end minus the beginning. We want to divide into 5 different rectangles, so it would just be 1. These strips divide the interval into n subintervals, so you don't really need to know this notation, but that's just what it's saying. Here's x sub 1, x sub 2, x sub 3, and so forth. Something that I really like to do, how I'm absolutely in love with my number line. When I look at these things and I want to determine if I'm using left endpoints and right endpoints, I don't like to draw the whole figure out. Sometimes I don't really know what the curve looks like. And so what I do is I say, all right, well, I'm going from 0 to 5. Okay, I want to make 5 different rectangles. So here's 1 rectangle, 2, 3, 4, 5 rectangles, right? Each of these, of course, the width is 1, so that's the delta x that we saw there. If I was using left endpoints, okay, then this is always my first rectangle. But if I'm using left endpoints, this is going to be the point that I use. And so you'll see how I use this in the future, but I'm going to just say here's the first, second, third, fourth, and fifth rectangle, because here are my rectangles. I don't really care where they are. But I'm saying, okay, that's what I would choose for my left endpoints. If I was doing right endpoints, though, my first rectangle, I want the right, I would start there. And so you're going to see me using this a lot more in the future and in the homework and stuff. But this is how I like to look at it as opposed to looking at it all on a graph, because then I have too much going on. If we're using right endpoints, again, this is just notation. You're going to say that your first endpoint, right, since we're using right endpoints here, that means we're using the right ones to draw the rectangles. So you're using the right point to draw the rectangle. Right point to draw the rectangle. The right point to draw the rectangle. The right point to draw the rectangle, we'll just go straight across. Right point. The right point to draw the rectangle. Okay? And so we're starting, of course, here. This is my R1, R2, R3, R4, R5, 6, 7, 8. There were 9 rectangles here. And so, of course, if I started at A, then my first endpoint for right endpoints would be at A plus delta x, because I'm using a right endpoint. If I was doing left endpoints, then my first one would just be right here. This would be my left endpoint. So I'm going to redraw with the left endpoints. So if I was using left endpoints, I would start here to make my rectangle. So the shaded is my left endpoints. Use the left endpoint. Use the left endpoint. Use the left endpoint. Just go straight across. Left endpoint. Left. Left. The left. The left. And so I would start at A. My second one would be A plus delta x. And so forth. Okay, so here's just more generally, these are all drawn with the right endpoint. Do you see that? That's right endpoint, right endpoint, that I'm drawing these rectangles with, the right endpoint. And so on all of these, I want you to try and draw in with the left endpoints what the rectangles would look like. So I'm going to go ahead and do that while you do it. And forget about the last one. It's too messy. So that's with the left endpoints that I drew in. Since the approximation seems to become better as n increases, we define the area of the region as follows, which is the limit, okay, of the sum, because we're summing all the rectangles, this is the sum, from I equals 1 to n, because we have n of these rectangles. F of xi, just like we saw before, is nothing but the height, and delta x is just the width. So you're summing up all of the widths times the height. Let A be the area of the region that lies under the graph of the curve y equals e to the negative x between 0 and 2. All right, so we're going between 0 and 2. And again, I'm not going to draw on the curve. I don't really care about what the curve looks like. But I know that we're going between 0 and 2. Use right endpoints to find an expression for A as a limit. So here we have to break this into n rectangles. So I can't really draw it as well. And I just have to do it very generally. I know that we go from 0 to 2 and we want to split it into n rectangles. And so the area is going to be, using the right endpoints, is going to be the limit as n approaches infinity, as I make infinite of those little rectangles. So I want to sum up all n of these, and I need to do the width times the height, or the height times the width, I guess, was on the other side. So the height is just going to be e to the negative wherever I am. So I am at 2i over n times the height, which is just 2 over n, right? Because if I split this into, n little sub-intervals, I can say that I'm at x sub I, x sub 2i, x sub 3i, whatever. So then part B, estimate the area by taking the sample points to be midpoints and using 4 sub-intervals. So now let me draw on this one. So I need to split this into 4 different things, right? So now I have something more concrete. I've got to split this into 4 different things. So that's going to be 1/2. Okay. But now I want to use midpoints. So this would have been left 1, left 2, left 3, left 4. This would have been right 1, right 2, right 3, right 4. But I don't want either of those. I want midpoints. I want in the middle. So here's my rectangles, 4 of them, and I want in the middle of them. So this is going to be my first one, my second one, my third one, and my fourth one. And so where am I? I'm at 1/4, just splitting it in half, 3/4, 5/4, 7/4. Okay, so to get my midpoints, I'm going to do the width. And so the width of this rectangle, don't get confused, it's still 1/2. And the height is f of 1/4, because that's where my first midpoint is. Then the width of my second one, it's 1/2. And where am I? I'm at 3/4. Keep going. And then I just put it in my calculator, really. I would just put all this. I would go y1 equals e to the negative x. And then on the home screen, I would do, 1/2 times y1 of 1/4 plus, all along, remember, by now, vars. Go over to y vars on your calculator. Choose one function. And so you should end up with 0.8557. The distance problem. Here our goal is to find the distance traveled by an object during a certain period of time if the velocity is known at all times. So again, we're going backwards. We're going from a velocity to a distance now. If the velocity is constant, then the problem reduces to the familiar formula, distance equals velocity times time. But what if the velocity changes over time? So let's just suppose we have an odometer on our car. It's broken. We want to estimate the distance driven over a 30-second time interval. Stay consistent with your book, how your book did it. They changed this to feet per second. Of course, we need to get this in seconds so that we're consistent here. And 1 mile per hour is, probably know this from the SATs, that 1 mile is 5,280 feet, and 1 hour, of course, is 3,600 seconds. So I'm just going to use that conversion. You don't need to do this. It's not really a big deal. But I'm just going to do that for you. Okay, so we're going to be using that information. And so the distance is the area under the curve. So we're going to denote that with this little squiggly, the antiderivative. And we're going to be using that a lot from now on. So I'm just going to use that to just introduce you to it. We want to take the antiderivative of the velocity with respect to time. Okay, so that's saying take the antiderivative of velocity with respect to time, and don't worry about the notation yet, just introducing. That is the area under the velocity curve. Okay, so if I'm using left endpoints, what do you get? So here are my rectangles. I'm just going to make as many as I possibly can. If I'm using left ones, here's the first, second, third, fourth, fifth, and there's my sixth one. I can't make any more than that. And so my width is 5. And my height, this is left. See, I labeled it left. I'm going to use the height as 25. That's the function at time 0. That was my f of 0 that I was writing before. The width of this rectangle is also 5. And the height is 31. Okay, I'm using the left again. So left, 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 left. Keep going. And that's it. I stop here because that last rectangle, and I want to use the left endpoint. And so I'm going to get 1,135 feet. What if I'm forced to use midpoints though? I just want to ask you that. Can my rectangles be the same? My midpoint would be in between. Do I have any data at 2.5 seconds? No. So if I am asked to use midpoints, I'm going to need to change my width of my rectangle. Okay, if I'm using midpoints, I'm just going to write it down here. These need to be my rectangles so that I have something in the middle. I just don't have enough data. So if I'm using midpoints, then I only actually have 3 rectangles instead of 6 rectangles. I have a lot less data here. And my width is 10. I go from 0 to 10. My width is 10. My height is 31. And so I get 1,200 feet if I was using midpoints. So here we're going to just sketch a velocity function of the car. So the velocity function of the car is sketched here. We're going to just draw rectangles whose heights are the initial velocities for each time interval. And we actually used left endpoints in our last example, which is what is drawn here. We used the left endpoint. You see the left endpoints are used here to draw the rectangles. And you can clearly see that we have an underestimate. If we had used right endpoints, we would have had an overestimate, right? Because if we had used the right endpoints, it would have looked like that. We would have gone over. So finally, we can just denote this all as the distance is the same thing we were talking about before. It's just the area under the velocity curve. The distance traveled is equal to the area under the graph of the velocity function. So the distance problem and the area problem are just the same problem. And that's it for this lesson.